I'll say this is my first time at this conference. I have to thank everybody. And first of all, I have to thank the co-authors, Domenico, Bonzo, PhD graduate student, and from Italian University. Let me start with very quickly with what I think why I'm here, because I think that probability theory is really the best framework for designing intelligent systems. I'm not saying that just because I think that this is a good idea to describe systems, but it's a good idea. Probability theory is a good framework.
We can't really hear you very well back here.
Yeah. Maybe I'll hold it like this. Okay, I'll hold it like this.
That's better.
I was saying not because I think that we can describe systems in probabilistic terms, but because we can design them. And we have countless examples in which, in signal processing, in computer science, we can use probability theory. Oh, you wish you? Oh, Lord. Okay, like this. Okay. Okay. But the real problem in using probability theory is that. Yeah. That's the first time. All right. But the real problem in designing systems based on probability is we have to deal with considerable model uncertainties. We're very good at solving models. Well, very good. Usually we use to solve models, but we have to deal with lots of model uncertainties. So alternative theories being proposed. Alternative theories probabilities. Some of you may have heard about fuzzy thinking, fuzzy logic, Dempsey-Shift theory. Dempsey-Shift theory. Now, well, I share with you some of these views, but one thing that we should be aware of is that some of these frameworks do carry a certain utility, so that they are very useful sometimes for people that don't know what to do, where they know very little about the model. And the reason why actually I stumbled into maximum entropy, because we're looking at a classification problem for a tracking problem, and I gave to Domenico this task of trying to solve the problem using Dempsey-Shift theory, which he understands, I don't. Looking through the literature, we found Ariel's paper, and we used Entropic Priors. And using Entropic Priors, we got exactly the same result that was being obtained with the Dempsey-Shift theory. So this sort of opened our eyes and tried to give us take a closer look at some of these problems. Of course, attribute to Jane's probability theory, logical science is like preaching to the choir here, but I want to also point out an interesting paper by Paris that talks about how maximum entropy really seems to make more common sense than something else. But again, this is probably preaching to the choir, seeing the community topics. So what I'm going to talk about the problem of priors in classifications, standard problem, and the problem of objective priors. So I'll show you two examples, and the problem of consistency with an example of conflicting experiment. Okay, so this is a simplified view of Bayesian inference. We have likelihood, we have prior, and I like to think that we're looking behind the curtain. So we have observations, and we're trying to get back to see. But we may not know what the prior is, we may not know what the likelihood is. In this talk, I will not address the problem of not knowing the likelihood, but just the problem of not knowing the prior. Before I do anything, let me show you an example. I know that there have been countless examples in this conference of inadequacies of prior choices. But we stumbled into this example, and I think it's very instructive. Suppose that you have two factories, and each factory produces objects of length between L1 and U1, L2 and U2. And you get an object which is of this length between L2 and U1. Obviously, the object belongs to the superposition, to the intersection of the two sets. So what do? We base, we set up two likelihood functions, pretty straightforward. So one is a little narrower than the other one. So we assume that that's the situation. And so if we get, the answer we get from Bayes' theorem is that the probability of the first class is higher than the probability of the second class. Just I want to emphasize, we really know nothing about this problem. And Bayes' theorem, based on the fact that the likelihood is higher, and it's normalized, gives us an answer which seems to contradict our common sense. Let me give you another example. Suppose we have three colors and we have blocks. So we have a triangle, square, and a diamond. So red can only be triangle and square. Green can be any one of them. And blue can only be a diamond. Okay, we set up this as a likelihood matrix, is a discrete space, and we look at the posteriors. Just look at what happens. This is the posterior, so given I observe a block, a square block, I get from Bayes' theorem that red is more likely than green. The question is why? Why? Is this an artifact of probability theory, or we're just doing something wrong here? Of course, what we're doing wrong here is to assume that the priors are uniform. So, the search for objective priors is an issue that has been debated many times in this conference, and please don't be too hard on me, because I'm just trying to make these things work. And okay, so uniform priors are very well known, objective priors, contrary priors, reference priors. I'll say something about reference priors afterwards, and other priors related to domain knowledge. Entropic priors. Entropic priors are proposed by many people in this audience. So please, I apologize if I don't give credit to everybody, and give me a hand in giving proper credit to everyone. And, in any case, I do believe that potential in signal processing are still to be explored. And we focus on a very standard problem in signal processing, which is that of pattern recognition. So we have a discrete hypothesis space, just like I showed you before. So entropic priors are obtained from maximization of the joint entropy. You can formulate this in terms of applied distance, but there's no need at this moment to be specific about this, because the results will be the same. And the entropic prior is just this, which many of you may have already seen, is the normalized exponent of conditional entropy. Okay? And when first time I saw this, I said, this is pretty amazing. We have Bayes' theorem with no priors. Okay, so Bayes' formula only with likelihoods. And this is something which came directly from Ariel paper, which we adapted to this context of packet recognition. So we looked in the literature and we tried to figure this out. And we asked some other friends in statistics say, but what kind of prior to check?
Wasn't there an alpha floating around there?
Alpha?
The usual form
Yeah.
of the entropic priors is an alpha.
Yeah, no, in this case you don't get the alpha because this is a discrete space. So there is no uncertainty about space.
These are not repeatable experiments.
These are what?
These are not repeatable experiments.
Right, okay, this is very simple linear combination. If you write the joint entropy as a superposition of conditional entropes, and you solve with a constraint optimization, and you get this. It's really a technical issue.
Can I come in on that?
Yeah.
So I glitched at the same point, actually.
Okay.
H is an extensive variable. You make the range bigger, then H grows, and that's repeatability is one part of this.
Yeah, well, I'll talk about that afterwards, because the repeatability issue is a question. Let's go through this and maybe we'll discuss it. So it's very, very simple. We're talking about a discrete hypothesis. C, it belongs to a discrete set. Maybe it's not clear from this formulation. C can only be C1, C2, Cn. So that's the reason why we don't have any normalization constant. So we asked for help to statistician friends, people that deal with this problem, and say, why don't you look at Bernardo's priors, reference priors. What does reference prior really do? They make a lot of sense. They try to maximize this distance, maximize the mutual information between mutual information between the joint density and the distance between the joint density and the product of the marginals. This is also the Kuba-Pleiber distance between the posterior and the prior, which makes a lot of sense. Trying to get the prior which is the farthest from the posterior. And this is a well-known problem in information theory, and the solution is obtainable using Arimoto-Blount algorithm. This is from Cover's book. It's something which we use very often to compute communication channel capacity. So maximization of the joint of the mutual information is the condition under which the exchange of information between C and X is maximum, and this is the condition of channel capacity. This is so the value is actually Shannon's channel capacity. So we try to compare these two things. And it makes a lot of sense. So it seemed to be the two most sensible things to do, and we did. So we went back to example 1, and we computed the uniform priors with the entropic priors. And we get 1/2 and 1/2. This makes much more sense than what we were getting before. So that not using the prior basically constrains the two distributions to become equally high. So it's not actually distribution, it's the product of the likelihood times the prior. So the two becomes exactly equally high. So that the posterior probability becomes 1/2 and 1/2. This makes a lot of sense. But what happens with the other example? Well, it's a little more complicated to solve it because we have to go through Arimoto-Blount recursions. And it's not too difficult, but requires a little bit of thinking. And also we have to do it numerically. So we have to do some numbers in this example. And so these are the results we get with uniform priors, with entropic priors, with maximum information priors, Bernardo's priors, essentially. I must say the reference priors are generally in the literature reported for large sample sets, and this is for small sample sets. So this is intriguing because this makes more sense to me than this one. But let's see the other example. The other example we get very similar situation. The entropic priors, which are these, the uniform priors are these, and the maximum information priors. Look at the entropic prior. The entropic priors equalize the posteriors, so they make equally likely. Say I look at a block, the block gives me equally likely red and green, and the same for the others. What max information priors do, they really essentially eliminate the hypothesis number 2. So they give all the weight to the first and the third hypothesis. Okay? This seems to be a bit of an artifact because it's like we're doing exactly the opposite case. But let me show you another example where we set up 3 likelihoods. There are 3 Gaussian likelihoods. And this is the result of the product of the prior with the likelihood in the 3 cases. In the uniform case, they remain just the way they are at the beginning. With the entropic priors, they are equalized. Equalized in fact. And with the maximum information priors, the third hypothesis becomes emphasized because it's the cleanest. It's the one that's the most differentiated by the others. These are the posteriors. So it's very intriguing to see this example because it looks like entropic priors are the solution that make more sense. But again, maybe I'm speaking to the choir here. And there are intriguing similarities to membership functions using fuzzy logic, where they use membership functions which are all equalized in the height. But this is something to be explored. Anyway, so what's the conclusion on Bayesian inference is that basically in determining the prior, the maximum priors seem to be what a good genie would tell us. So it would help us in doing the inference process, so from observations to get back C, which makes sense from a communication point of view. And the entropic priors are the demon. The entropic priors are trying to screw things up. This demon is trying to mix things around behind the curtain. But the topic of the paper of this conference is really to apply priors to sequences. Let me give you a simple example. Suppose I have 2 superimposed uniform distributions, and I get samples from the intersection of these 2 sets. So I get this sample, I get this sample, I get this sample, and the uniform priors give strong preference to class 1. Of course, if I get a point in one of these 2 sets, the posterior would be okay. It would converge this problem to the proper class. But what happens while I'm still in the superposition set? This may be critical in some application where we have to be reasonably certain before taking a decision. So, for stochastic sequences, we reformulate the problem, and the problem is reformulated assuming that this is a sequence, and this is the posterior. Now, the general formulation of the posterior should be that the prior, which is a function obviously only of C, depends also on n, because n is the size of the sample set. So this perhaps answers some of the questions that you may have in a little bit, and I know you will have a lot of questions, please don't kill me. But anyway, so in general, the prior should depend on n, because it depends on the joint entropy of the whole set of x from 1 to n. What is the problem? The problem is that using entropic priors the way they are, they converge to the wrong class. They might converge to the wrong class, because what happens is that the prior determined by the entropic prior formula, the prior really represents the volume, the normalized volume of the set, of the typical set. It's a typical set for 3 classes. And then as you grow, things grow, but the class with the largest entropy always dominates. And therefore you get a convergence of the prior to the class with the maximum entropy, which may not be your answer. So what to do about this? Katic and Priors suggested to constrain the average of the entropy. This may be a solution, but the question is, can we find a self-contained approach? Can we somehow come up with something that does not require an a priori information? So bottom line is we can accept degenerate priors as far as we maintain posterior consistency. So even if the priors diverge the way, well, they converge to the class with maximum entropy, can we somehow get posterior consistency? Posterior means that if the data is generated from class Ci, the posterior converges to the right class. And this is a little more technical, but if we use generalized asymptotic equirepartition property, we can show that there are some technical details for the correlated case. For the independent case, this is pretty straightforward application of the law of large numbers. We get this type of convergence. Then if we use it and substitute it in a base formula, we get the consistency is guaranteed if the prior are such that this condition is satisfied for every pair. Okay, D is a Cooper-Platter distance. Divergence, I should say, it's not a distance. So the posterior probability and entropic priors are consistent if this is a sufficient condition. We haven't proved the necessary condition, but as a sufficient condition is very useful anyways. That basically the conditional distributions don't have to be too different in terms of their conditional entropy compared to how much they are distant one from the other. Okay. And many stochastic processes, fortunately, do satisfy these conditions. And unless you have a very superimpose means that supports, this condition is easily satisfied. We have applied to Gaussian processes. This is pretty standard Gaussian process where the entropy and Cooper-Platter distances are easily computed. Obviously, it says stationary Gaussian process. The base formula, the condition can be reformulated, and quickly go through this. And AR processes are just a class of stochastic processes. Just a simulation shows how 3 processes, 3 AR processes, 2 AR, and actually a white processor are satisfying the heuristic condition for n that goes is beyond 2 or 3. So basically, as far as the processes are not superimposed in terms of their poles on the unit circle, they are okay. And then this is what happens with the posterior, the evolution of the posterior. Generally, the entropic posterior tends to be much more cautious than the uniform, the posterior with the uniform. But I wanted to try something a little bit more difficult, and it's a coin flipping experiment. It turns out that coin flipping experiment is a tough one because the condition for conversion is not satisfied. This is a setting up n possible unfair coins, and the coin flipping n times independently. The standard compute the entropy, the apply the distance, and look at the consistency condition. And if you go through this, I don't want to go through it in details. So for m greater than 2, so 2 different coins, more than 2 different coins, the posterior consistency is not guaranteed. So what do? We can use constrained entropic priors and set this up with the condition that we derived before, which is unfortunately the linear condition, as a standard optimization, and using standard techniques from optimization, we can find a constrained entropic prior solution. Essentially, the lambda multipliers here have to act to try to reduce the spreading of the entropy towards the class that's the one with the largest entropy. And simulation very quickly, because I don't have much time. So we considered 3 coins. 3 coins, so the coins are biased. 1 is not biased, and 2 are biased. And the unconstrained entropic priors, you see they are the one with the continuous lines, they diverge. Also the constrained entropic priors diverge, but they're much contained in their spreading, because we're trying to get consistency in the posteriors. And if you look at the posteriors, in this experiment where we have generated data from coin 1, fit 4 times this set of posteriors. I don't know if you can see it, but this is the uniform, the one, the very light one. And the constrained entropic prior, well, I want to point out that the unconstrained entropic prior converge to the wrong class. Okay, so they don't really work. Instead, the constrained entropic priors converges to the right class. Obviously, this is useful for small n, because for large n, the uniform priors work just fine. Okay, I know you have a lot of questions. The conclusions are quickly. Entropic priors in signal processing, I think they qualify as an excellent objective solution where only likelihoods are available. There's plenty of situations in which we have only likelihoods. And the posteriors reflect much more common sense lost when we use uniform priors. And we have to consider the consistency problem. We have applied entropic priors to Gaussian processes, and future work will be on vector processes on certain likelihoods and continuous parameters. I have some ideas on how to do continuous parameters. I would love to collaborate with any one of you that may be interested. Thank you very much.
Hi. Very nice to see all this sort of development and stuff. Have I got you right that in your example of 2 factories, if you get a measured the length which is in the intersection, you don't care which factory it is?
Yes.
What
With entropic priors.
Yes.
Which to me was remarkable.
Let me give you something which might give cause for concern. This mug, this mug contains liquid. Okay, it's been drinking it. It's either water, which is liquid between 0 and 100 degrees, or it's his favorite tipple of synthetical, which is liquid between 23 degrees and 24 degrees. I stick a thermometer in this, and it registers 23.4 degrees. Now, that's almost a real probe saying this is synthetical, because 23.4 degrees is quite unlikely on the water hypothesis, but much more likely on the synthetical. So I don't want, in that case, to be half ambiguous between water and synthetical.
Yeah, because you are automatically injecting into your problem your prior choice. So whether your prior choice is a good prior choice, you are doing that, because when you look at the problem and you recognize that the likelihood, the highest likelihood is the one who corresponds to the most likely answer, means that you are injecting your uniform prior in it. And I think the entropic prior really tells you what the answer is when you know absolutely nothing about the prior. And I'm amazed by the results of this experiment. It's very simple. When I saw some of these ideas floating around, and I think that, but there is a gray area there. The gray area is when you have prior knowledge, how do you inject that prior knowledge? But if you have no prior knowledge, I'm pretty much certain that the entropic prior is the solution.
Next question.
So this is really just a technical clarification. I know that you're not advocating the uniform prior here, but I'm used to looking at problems where, and I think it's true in this case, the uniform prior is impossible to define uniquely because there's no preferred metric to define uniform. Is that the case here, or is there some unique uniform prior that I've missed?
Maybe I didn't mention sufficiently, but the solution of the entropic prior in the case of classes that have the same conditional entropy is the uniform. So the entropic prior is really a generalization of the basic formula.
Really, I'm just asking how you define the quote uniform unquote prior here.
Okay, it's probably not very clear in the slides. I have to apologize because it was implicit in the formulation that C is a discrete variable. So it can only be one of n.
Okay.
Okay. So this is basically a number. Okay.
Thanks.
Okay.
Thank you, Francesco. I think it's very nice to see people working on these things. It's very nice. I agree with you on many things. For example, you correctly pointed out that entropic priors are priors that often used when we really are very ignorant about what's going on. We only know the likelihood. Most of the time when people are doing experiments, they know way more than this. So be careful with entropic prior because you may know way more already.
That's the case. It's examples.
Don't use entropic priors blindly because you may already have way more relevant information than we may think. So be careful with it. But you're correct. If you only know the likelihood, that's the way to go. I also agree with you completely that unconstrained entropic priors, which is what you have there, are really leading you to wrong prediction. So it is crucial to obtain an appropriate constraint that will lead to reasonable results.
But let me say, the unconstrained solution does work sometimes. Because even though you have convergence, the prior always converges to the one with the largest entropy. The posterior converges. Posterior converges.
In any case, with Roland Preuss, when we did this work, the challenge was to say, when we have experiments that can be repeated indefinitely, is there any piece of information that we could from that we could also incorporate? And the piece of information that we included is the fact that if you can perform an experiment many times, if you can perform an experiment n+1 times, and for some reason you forget what the result of the n+1st time was, you forget the last result, then informationally you're in a situation which is completely equivalent to having just n experiments. So if you have n+1 and you forget 1, it should be the same as n. That was the kind of additional piece of information that we put into the problem that was beyond just the likelihood. And it was that piece of information that led to an infamous alpha factor that then we have to worry about and all that. So it's very interesting that you do not use that kind of information. You use a different kind of constraint.
Yeah, the real reason of the difference is that I really haven't ventured myself into the case in which C is continuous, which is the case that you address. Because when C is continuous, things become much more complicated. You have to use differential geometry, and I have some ideas on how to do it. In fact, the coin example which I showed is...
But I guess I'm addressing the fact that
we're going to have to end the conversation. We're going to have to end discussion on this.
All right, thank you.
Thanks.